Hello, welcome to the live session of Quantum Technology and Quantum Phenomena in Macroscopic System. I hope all of you are enjoying the course so far, and I received a lot of queries regarding certain concepts, and also we got queries regarding the assignments, and those assignment queries has already been taken into account by my TAs. Today in this live session, I will try to answer to some of your queries, and if you have more queries, you please feel free to write it in the chat box. Now let me answer to the queries that you have sent me in the course website. Okay, so I will start. I have prepared a PPT in this regard. So let me answer the queries from there. Um, right, this query is from Dept Gusait. He asks, is from IIT Ropar, and he asked two very interesting questions regarding coherent states. His question first question was, as coherent states are not eigenfunction of a Hermitian operator, it's an eigenfunction of the lowering operator. As we know, we have coherent states in reality, is also not a normalizable. Okay, he's saying coherent state is also not a normalizable state. So how and why we can realize a coherent state in a system? And his second query is also, what does this coherent state mean physically, and what is its physical significance? All right, I already actually I answered to his queries via email, but I think the question is interesting, so let me give a little bit more elaborative answer here. As you know that this coherent state is the most classical quantum state, and it is the way it is defined. It is defined as the eigen state of the annihilation operator. And you know that annihilation operator is a non-Hermitian operator, and rightly so, the value alpha, which is a number, it's a complex quantity rather than a real quantity. So that's why it may be a bit confusing that how come then it is a physical state. I think if I have understood your question correctly, I think this is what may be confusing you and maybe a lot of people. Okay, now it's all right that it's an eigenstate of the annihilation operator, but if you look at the equation here, what it says is something very deep. What it says that in spite of the fact that you are annihilating something, and in this case it is a photon. If I talk about electromagnetic wave, quantized electromagnetic wave, if you annihilate one quanta or one photon from the electromagnetic wave, it still maintains its character, that it still remains a electromagnetic quantized EM wave. Its state remains maintained. That's what it means. Okay. Uh, what does that mean? And you see the word coherent is associated here. That means the phase is very, very well defined. Now, because the phase is very well defined, and the number of these, and as I said, this is most classical state, the number of quanta involved here is extremely large. Actually, it is infinitely large, and you cannot actually measure the number of quanta to 100% accuracy, because there is an uncertainty relation between the number of quanta and the phase. That means if you know the phase for certainty, then there is an uncertainty in the number of quanta in the coherent state. So that's why you may not know. It's basically, as you see, coherent state is a superposition of number state. It is not a number state. And when we talk about number state, if you as I taught these things in the lectures, when say we have this K0, K1 and so on. K0 means there is no quanta in the state. K1 means there are one quanta in the state, like that. But here in the case of coherent state, there is a superposition of number states. So there is an indefinite number of quanta is there, and thereby the phase is that way kind of fixed. And laser is a prime example. The quantum state of laser is a coherent state. So if you think little bit deeply, you will understand that okay, yeah, it is. And as you know that yes, indeed we can produce laser, and laser is completely, it's a physical object. So I hope you get the idea here, right? So let me go to some other queries. Next, a lot of comments, feedback I received in the website. Then you see, okay, this is actually from first week itself. I noticed it later. One comment was this, that care must be taken about notations. I am noting many mistakes like calling a k to a wave function, calling a kth a wave function, but kth wave functions are completely different. So this is basically from week 1. Yes, I do agree here, and we are not being very rigorous here, but and we are using this whether it's a kth state or state vector and wave function a little bit in loose sense. But the fact remains that when I talk about a quantum state or wave function, all the information is actually contained in the state vector or the wave function, and there's a the subtle difference between the state vector and the wave function. You know, kth or the state vector is an object in the Hilbert space, and when I talk about state vector, next. Right, you see, you represented it by a state vector like this. It is Dirac, in Dirac notation. This is kth psi. This is a state vector. Next, and the wave function, we can represent this state vector either in the x representation or in the p representation. When I say represent it in the coordinate, so this is the wave function in x, and then it has a momentum representation also. Thereby you can get all the information about its position and stuff like that is contained in this function. This is the wave function. Okay, that's the basically subtle difference. So next, yeah, uh, this is the momentum wave function. All right, and as you know, as such, it's a complex quantity, and it cannot be measured because of that. And as you know, according to Born rule, Max Born interpretation, what it has meaning is that if you take the mod square, for example, if you take the mod square of this guy, that means, I think this is very, all of you know that mod psi x square basically gives you the probability. Okay, 1 minute, this is right. This gives you the probability as you are in the state psi, and then you want to know what is the coordinate of the particle or the system where it would be. Then if you take the mod square, that gives you the probability of getting the system or the quantum object in position x, right? This is similarly you can interpret about the momentum wave function. Okay, next. Right. So the main point is that all information of a quantum system is contained in the quantity psi, and it's a complex quantity and can't be measured. All right. Then another feedback is that if you can provide the transcript, it will be very helpful. Yeah, I agree to that, and in fact, we are working. Work is in progress, and you'll be given the transcript. I think already some initial lectures transcript may be available. Work is going on. And also another query is, please provide sources or questions regarding two-level TLS, that means two-level system, I am finding it difficult to understand the application of theory in questions. Any book or reference material where I can solve numerous questions on newly introduced topics in the course would be okay. I understand that would be helpful. Yeah, I have. In fact, maybe in introductory lecture, I have already given you the source that from where I'm picking up the materials, and still today also I am going to provide you some sources for separately for module 1, module 2, and module 3. For two-level system, there's a good book by very elementary book, I would say, that is by Mark Fox, published by Oxford University Press, that is called Introduction to Quantum Optics and Introduction. And also you can look at Griffith's Quantum Mechanics. That's very easy book. You can learn all the things about two-level system, and maybe some other materials I will also provide you as you later in this PPT. I'm actually noting it down some more materials. Okay, another query. Actually, feedback. Can you provide lecture notes for each section? Provide notes for respective lectures. Yes, I'm working on it, and hopefully I will share the notes gradually. Actually, that would be basically the ones that I have written in the lecture note, but maybe I will organize it a little bit in a more better way. Maybe I will make some more detailed comments there in the notes, which is not in the there in the live in the lectures that I recorded. So this I will try to provide you. Okay. All right. Then next, yes, one query is that course is too much mathematical. Yes, that is meant to be actually, because the whole objective of the course was to prepare you for to familiarize you with this new research area. It is at the frontier of research nowadays, and you must have to learn certain mathematical and theoretical tools to understand what's going on in the area. So keeping those things in mind, maybe some of you may be interested in doing research, or maybe you would like to understand scientific literature in the area. For that, this is, you can consider it to be kind of preparation. So enough material is provided in the whole course, and once you complete the course, you will actually realize, then you will be able to read papers, scientific papers from top journals, and hopefully you will be able to make sense of those articles, and who knows, some of you may actually contribute to the area also. All right, next. Yeah, one comment is that the topics are very interesting and the lectures are very nice. Okay, so I really thank for this very beautiful comment. Um, Now, right, so next, okay. Now here are the materials. Some of these materials I have actually shown in my introductory lecture. As you can see, there are the book where you can get a lot of information, very elementary and very little mathematics, not very rigorous mathematics is used in the book by this Quantum Optics and Introduction by Mark Fox. This is published by Oxford University Press. This book I will recommend very highly for module 1, whoever is facing trouble with mathematics. Okay, this will give you a lot of conceptual inputs will be given there, and hopefully you will enjoy this course. It's written in very easy English also. Another book is Introductory Quantum Optics by Gary and Knight, and this is from Cambridge University Press. This is also a very nice book. There are a lot of problems are there. You can, I think one guy asked about that he wants to a source where he can do a lot of problems. So this is the book for you. Okay, and there's a very very elementary another book, that is Quantum Optics for Beginners, that you can also look, at, and it is also very nice, and very short chapters are there, and maybe you can enjoy, you can read that. Another book, little bit of on the higher side, Introduction to Quantum Optics by these three writers, Gilbert Greenberg, Alain Aspect, and Claude Fabre. These are French people, and maybe this is also Alain Aspect is one of the pioneer in the atomic physics or quantum optics area in experiments. So he comes up with lot of experimental insight in case if you are interested in experiment. So this book is good. Quantum Mechanics by Jet Li. This book, there are huge number of problems are there, a lot of solve problems are there. If some of you are facing trouble in Dirac bracket notation and things like that are related to that problem, this book is for those people who can really derive benefit by going through this book. And Griffith's book is, I think, well known. And there is a higher side, there is another book, a Modern Quantum Mechanics, that is by Sakurai. Mainly it was written by Sakurai. So this book is a classic, but it is on the higher side. If you want, you can go through that also. Okay, now let me go to module 2 next. All right, here, unfortunately for module 2, not many materials are there. As such, books are not, I'm not aware of any textbook kind of thing, so you have to rely on research materials, and there is a extremely nice and beautiful review article is there, very detailed review article is there, that is in review of modern physics. If some of you are unable to access the journal site, then this is available in archive also, so you can go through this. This is circuit quantum electrodynamics. Some of the materials in the course is from this particular review article. Next is there is a set of lectures are there, that is on this is Lou House summer school was there. They organized some schools and lot of pioneers gave talks there in various areas. And next please, if you there is a chapter, third chapter of the book, that is related to circuit QED, and he is basically giving talk. This lecture is by S.M. Girvin. As you can see, that circuit quantum electrodynamics, this particular review article is also written by S.M. Girvin. So the same guy, but this set of articles are, this notes are easy to read. Okay, you can go through this. Now, material for module 3, again, in that same summer school, there are, next please, if you will see that in chapter 8, there is a chapter on quantum optomechanics. This is a basic chapter by, written by Florian Marquardt, and a lot of materials in module 3 is taken from this, his material also, Florian Marquardt. You can go through it. And there is a book called Quantum Optomechanics by Milburn and Bowen. Milburn is a theorist, Bowen is an experimentalist. So you can, this is little bit on the higher side, but once you finish the module 3, you will be able to actually read this book and you will definitely enjoy. You see, what I have done in the whole course in module 3, I am trying to become very as detailed as possible. Sometimes you may find that there is too much of mathematics is going on, but if you can actually suffer through that, you'll be in a gaining position, believe me that, okay? Because ultimately my objective is different. It's not to take you through some easy stuff, and that would not be, because if you really want to do some good stuff, you have to go through those lectures patiently, and I think this will help. Next, there are some other materials also regarding module 3. This is a bit on higher side. One is on cavity optomechanics. This is edited book. It is written by a lot of experts in the area. A lot of chapters are there. If you want to know what's going on recently in the area, this book will give you a lot of idea. So, and there's a review article is also there. Actually, I mentioned it in my introductory lecture also. That is cavity optomechanics. This is written by Espelmeyer, Kippenberg, and Florian Marquardt. And there is another one that is, it's a very basic article and very nicely written. This is also, you can find it in net. This is by Pierre Mestri, a short walk through quantum optomechanics. I think these are enough materials are there, you can go through it. Somebody asked me for reading materials. I think these are what you have. So please do register for the course and appear the exam. The certificate, I think it's going to be very valuable for you. It may really help you a lot, and please do register. And I will take another live session sometime later this month. So I will really appreciate if you can post questions in the web page, and if you really want that certain small concept, those things has to be more light should be thrown into those concepts. Maybe I will, in the next live session when I meet you, I will try to give you some kind of presentation on those small concepts. All right, so your comments will be highly appreciated. So thank you so much for attending. As I can now see that so far, no, okay, there is some queries. Okay, let me. Okay, you are writing, is it possible to implement quantum computing phenomenon without help of superconducting material? This question is by Ajay. Yes, indeed, there are. Actually, you see, there are a lot of other platforms are also there where people are trying to. Actually, there are at the moment. If you have gone through my introductory lecture, maybe I mentioned it there, or if not, you see, there are 3, 4. Routes are there where this competition is going on, that by this particular road, one is the using photonic qubits, right? Photonic circuits. People are trying to have realized quantum computer. One is the superconducting qubit is there. And out of all these things, superconducting material or that thing is the most popular one, because as I said, that all the technology is already available. Computer lithography and these things are there, and it is very easy to use those technology to fabricate circuits, quantum circuits, and so on. That's why, as far as I know, that this is the most prominent platform, and this is also the reason why in this particular course I am giving more emphasis on circuit QED and cavity optomechanics, because these are very easily realizable. And this Google's computer, quantum computer is basically a good example of this. Perhaps we have actually talked about it in module 2. Okay. And since you have done time evaluation of an A operator, that is old one, then how time evaluation of old A operator can be equal to new A operator? I'm not getting what you are saying. Time evaluation A operator. Okay. You can consider this annihilation operator to be kind of associated with the, okay, you can relate it this way. As I said, that coherent state is the most classical state, right? The coherent state is a quantum state, and it is most classical. So in that sense, you can consider this A operator, right? That operator, because it is non-Hermitian, so it has as such no physical representation or physical variable that you can associate with the classical one, right? Because as you know, for every physically observable quantity in classical physics, there is an operator in quantum mechanics, and that is Hermitian. Now here you are having an operator that is non-Hermitian, that is the annihilation operator, right? So this annihilation operator, you can consider it to be, here A can be analogous to amplitude of the electromagnetic field. Okay, that way you can look at it. So how this amplitude is evolving in time and things like that, that's how you can maybe you can get a connection, if I have understood your question properly. Right, A evolves in time because as you have seen that A is what? You had that A is equal to, A of t is equal to A of 0 e to the power minus I omega t. That's how it gets evolved, right? In phase space, we already discussed that when we talked about the coherent state, alpha, that quantity alpha is a complex quantity and its real part is related to position and the imaginary part is related to momentum in the phase space. If you please go back to our earlier lectures in module 1, I think you will get the idea. All right. So if you have more specific something to ask, please put that question in a more proper format in the website, then I will go through it and I will try to answer it, okay, in the next live session. First comment, okay, sorry, you said you missed the first comment. What is the first comment? Oh, okay, you are writing, I have a question regarding squeezing operator. In defining squeezing Hamiltonian, what are right hand side A and A dagger operator? Are they all or new operator? Okay. They are actually the new operators. Okay. They are the new operator. Yes, I think so. I think so. And what you are writing? Sorry, what happens to the entropy of atom and Barth system with dissipation? That is actually, we are not discussing what happens to entropy of atom plus Barth system with dissipation. Okay, this question I have to think. Okay, 1 minute. It is asked by O'Toole. Right. Entropy, okay. In entropy plays somewhat important role because certain quantities we can calculate this. You can use this entropy quantity for our study of entanglement. Maybe I will touch upon this in one of the lectures in module 3. How this entropy, because that's basically you can talk about the order in the system and whether a system is getting entangled or not. It is related to it is related to quantum information as well. So I think I will try to answer this question, honestly speaking, maybe a little bit more maybe in the next live session. It's a good question. I will note it down. Okay, what happens to the entropy of the system? We have not addressed anything like this in the course actually. It's a good question. Right. So, right. Any more question? So I think a Google Sheet is provided to you, and where you can put your questions, because so I just can't say something wrongly here, honestly speaking. If you post this question beforehand, because this is a research level subject, and though I'm working in the area, so sometimes what happens is that I need a bit of time to answer certain things. So it will be very useful if you can post questions in the Google Sheet beforehand. That would be I will try to answer. Okay. Next live session will be announced soon, and please try to put as much question as possible. I would not mind. Try to do. I will try my best to answer. Okay. Okay. Any more? Is there any? Sir, I have heard Google say it's really supremacy of quantum computing. Can you elaborate this briefly? Okay. Actually, why it is say the word supremacy basically means that this quantum computer can do something which classical computer cannot do. And in this case, they have come up with one particular example or computational job that the quantum computer could do, which a classical computer would take years. So, it will take lot of years to compute, do that calculation, and they have just got the one successful run they got, and based on that they're saying okay, because earlier people did not believe that it is in the first place it is even possible to build a or realize something like this quantum computer. So they have actually crossed the first barrier in that way. And to get as per my understanding goes, if you really want to have a good quantum computer, you should be able to manipulate lot of qubits. Okay, at the moment Google computer was able to manipulate only 52 qubits or so, but if you really want to do useful stuff, you should be able to maybe lakhs of qubit, maybe 10,000 qubits, depending on the problem that you are attempting. But the trouble is that it's not that easy, because when these qubits are talking, right, you have to be many times you should be able to create a kind of superposition state. I'm just telling you in a very layman kind of a language here. It's not getting very rigorous. You have to be hold that superposition state for some amount of time, okay, so that you can get something useful out of it. But the problem is that you cannot hold that superposition state for long time or for useful amount of time if you are having a huge number of qubits, because these qubits will interact with and that itself in such a way. There is something called decoherence, which you may have already learned, or that this superposition state will actually decay and it would not be possible to get anything useful. As the number of qubits go on increasing, the decoherence is also accordingly going to get increased. And of course, the people are trying to circumvent this particular problem. They are trying to, and research is going on. That's the reason this area is so interesting, and people are coming up with a lot of schemes and things like that, so that they can actually address this decoherence issue at least. So that's what my understanding right now. Okay. What you are writing? In Josephson junction class, while defining 5 S's, how n can be negative. Okay, since okay, you are actually, when I say n negative, that means you can consider it to be, suppose a Cooper pair is going from the upper island to the lower island. Okay, then I say that, you see, you can consider it this way. That means there is one Cooper pair is getting now missed, or there is lack of one Cooper pair in the upper island. Then there is a addition of one Cooper pair in the lower island. So you can, that absence of one the Cooper pair in the upper island, you can consider it to be negative. N is getting negative there. So n is equal to -1 means that one Cooper pair is getting what is called missed there, or one less Cooper pair is there, and one additional that Cooper pair is now getting migrated to the lower panel, and vice versa. That's how it is. Okay, so that is basically the convention. Okay, I hope you get the idea here, right? Uh, okay, I think. Okay. Yeah, time can be negative means, you see, when I say you are going from infinite past, okay, rather than taking it zero for many purposes, for even computational purposes also, you have taken that, okay, you have started something very long back, and at a given instant of time you are here, and from here I have suppose I have started the, I'm trying to give you a very elementary way of answering it. So if suppose at this given instant of time you have started some, you are trying to see the evolution of some system. So you are going from say 0 to sometime say 10 second up. Okay, what is happening there? But before that, what happened? You can just address it by you are going from say minus infinity to this, and sometime if you take the time integration from minus infinity to plus infinity, that's how it helps. Though the function as such from minus infinity to 0, the functional value may be 0, so it's not going to contribute. So that's the way you can think it, right? Okay. Okay, I think this will go on, and I will write any more question. All right. So we'll meet. You please study the lectures. Uh, Whatever is already posted, please do that, and please post the questions. Any conceptual issues that you have, please post it on that Google Sheet, and I will try to answer in the next live session. And next live session will be happen after another 2-3 weeks. So I will try to answer. Maybe I will prepare a presentation and try to address all your queries. Okay. So I think. Thank you so much for attending this live session and throwing questions at me. But please post questions in that website also, and I really appreciate if you register for the exam. Please, exam would be very easy if you are doing the assignments, and if you are going to the lectures, it would be very easy affair. Okay. Okay, then. So let me stop here, right? Thank you so much.